My name's Damien George. So I'll just give you a very brief background on myself. I used to be a theoretical physicist working in sort of string theory related topics, but I also did a degree in university in computers and engineering. And actually I was on a RoboCup team many years ago, maybe 8 years ago, working with Sony four-legged dogs. So you might have seen that yesterday. It's a lot of fun working with that. So during my time as a physicist, I got a bit sidetracked and rewrote Python to run on microcontrollers, and now that has taken over my time, and I'll tell you a bit about what I did there and how it's going. So don't forget to rate the session at the end. Now, the idea behind MicroPython is that electronic circuits, little microcontrollers nowadays, are getting very, very complicated, just like computers are. And there's a lot of functionality in a tiny little chip. And in order to get the most out of these chips, I thought it would be good to have a higher level language other than C or assembler to program them. So the idea was to see if it was possible to put Python on a microcontroller, to make Python small enough and use resources not so intensively so that you could use it as an application language on a microcontroller. So we all know that high-level languages like JavaScript and Python and Ruby have helped immensely in the development cycle of coding. So, you know, if you want to write a quick script, you write it in one of your favorite scripting languages, and you get something done in 5–10 minutes. And maybe that's all you need to do, or maybe you then rewrite it in some other language like Java or C++ once you've tested out the idea. So languages like Python are good for prototyping, but also sometimes good enough for the final product if performance is not a big issue. So the same concept can be applied to the microcontroller world. So microcontrollers, as I said, are getting more complicated, and they're at the point now where they have just enough resources to start running these scripting languages. And the reason that it's not an easy thing to do is because, well, the amount of RAM, for example, is about 100 kilobytes. So in 100 kilobytes, you have to do everything. You have to have a stack and a heap and all your data. And to have a language like Python run in 100 kilobytes is not easy. So for a bit of the talk, I will discuss exactly how it works, how Python can run in such little memory. But first of all, so why did I even choose Python to go down this avenue with? Well, I mean, I like Python. It's a very nice language to use, I think. It's a very high-level language, and it has lots of really good features like list comprehension, for example, and generators, and very good exception handling mechanisms. One of the big, I think, points for Python is that it has a very big community that is very friendly and very helpful. There's a lot of online resources for learning. I think Python is also actually a very easy language to learn. Maybe you don't like the idea of white space and new lines and indentation being instead of curly braces, but you actually get over it pretty quickly, and it's nice and neat, I find. And I'd say Python has a really shallow but long learning curve, so you can jump on very, very easily, and you can walk along, and you can start learning new things, and you get more and more productive. But it keeps going, this learning curve, because there are so many libraries and so many things you can do with Python, so many advanced features, that as a developer, you never really get bored with the language. There's more and more sophisticated things you can learn in order to make yourself more productive. And I think it's actually one of the more ideal scripting languages for microcontrollers because it has native bitwise operations, for example, like AND and OR. And when you're working with microcontrollers, you're working with bits, ones and zeros. So being able to do bitwise AND is really important. Unlike, for example, Lua, which doesn't have those kinds of constructs. It also has a very good distinction between integers and floating point numbers. So if you have an integer type, even though it's dynamically typed, if you have an integer and you add 1, it stays an integer. And you can keep adding 1 because it has transparent transition to arbitrary precision numbers. And if you have a floating point number like 0.5, then that stays a floating point number. And that's really important in microcontroller context because sometimes you need a 32-bit number and you need to actually have the precision of 32 bits. In contrast, say, to JavaScript, which everything is a number, is actually just a double precision floating point number. So if I keep adding 1 in JavaScript, eventually I can't add 1 anymore because I've got like 10 to the 100 plus 1 is still 10 to the 100 when you've got a double precision number. But in Python, if you keep adding 1, the number grows and grows and grows. So having this precision with respect to types, I think, is very important in a microcontroller setting. There's also, because Python is compiled, you have opportunities for optimization. As you know, with JIT engines in JavaScript, there's a lot of things that can be done there to improve performance if you need to. So I guess the big question is, why can't we use existing implementations of Python, which is called CPython because it's written in C, and there are a few other implementations of Python. So why can't we just take one of those and compile it for a microcontroller and just run it on the microcontroller? So the reason is that these existing implementations are quite intensive in terms of memory usage. For example, a single integer object, because it's an object, it carries around lots of information, like it's pointed to its type, a reference count, and the actual value itself. So the number 1 in normal Python takes up about 16 bytes of your memory, and it has to live on the heap because it's an object that can have extended lifetime outside the current function. So you have to, whenever you're doing 1 plus 2, for example, you've got lots of memory you need to allocate, and it's also rather inefficient. Well, to get around that inefficiency in CPython, when the interpreter starts up, it actually pre-allocates all the numbers from -5 to +257 because they're the most commonly used numbers, so that when you add 1 plus 2 equals 3, the objects already exist there, you're just referencing different ones. But nevertheless, if I'm pre-creating all of these integers, that's using about 4 kilobytes of memory just when I start up to make numbers. So this is not an efficient way from a microcontroller point of view, because that's 4 kilobytes of memory just wasted. That could be, half of your memory. So that's one of the a very big reason why you can't just take normal Python. The other one is that if I wanted to do a method call, so in Python things are mostly objects, so if I have an LED object and I want to turn it on, so LED.on, what I actually have to do is to get the LED object, look up the on method, and extract that, and then it makes a bound method object which binds the on method to the LED object, and then you actually call it. So in that call, you actually have to create an intermediary object, which is the bound method, taking about 20 bytes as written there. So just to set the LED to some intensity requires about 36 bytes of RAM to store the number and to store the bound method object. And this, apart from using up memory, it's also not good from a sort of speed and efficiency and determinism point of view. So if I'm running my code, what if I can't allocate on the heap? I have to do a garbage collection. That's not good if I just want to turn a light on. So there are things like this which make it hard to run normal Python on a microcontroller. And then there are other things that use heap memory, like for loops, for example. Okay, so I had this idea then to rewrite Python from scratch. And I also had the idea that I wanted to do a Kickstarter project. So Kickstarter is this crowdfunding platform where you pitch an idea and people give you money to fulfill that idea, or hopefully fulfill the idea. So I had these two things, MicroPython idea to put on a controller, and just to see what doing a Kickstarter was like. It took about 6 months to go from the initial inception of the idea to the actual launching of the campaign. And that was in 2013, so about 3 years ago, 2.5 years ago. And after about 6 months of actually working on this, I was thinking every day, oh, someone's going to beat me to it. Someone's going to write Python in a different way for a microcontroller. Because when you're in the middle of an idea, you always think it's the greatest idea, and everyone else is going to beat you to it. So it was like one weekend to make a video for Kickstarter, and then you publish it to Kickstarter, and you say, yes, I just want to get this out there. I'm sick of working on it now. I just want to see if it will succeed. So when I pressed launched the project, I was quite relieved to have this thing out there. But then that's actually when the hard work starts, because you have lots of people contacting you, and it gets sort of more and more intense as the time goes on. Anyway, but the Kickstarter project was very successful, and we got almost £100,000 and nearly 2,000 people pledging support. And I think they were just excited by the idea of some of the sort of cool technology that MicroPython was bringing. I'll explain a bit about that in the next few slides. But yeah, it was a very overwhelming response for me, and but really great to have such a project. And it was fulfilled after about 1.5 years, about 2 years since inception. So in 2015 in April, I called it officially done. So I'd finished all of the rewards and said that was it. I mean, that doesn't mean the project finished. MicroPython keeps going, but the Kickstarter itself was finished. But just as a note, so Kickstarter itself has so far funded $1 billion worth of projects. So they've taken in $1 billion and given it out, except they keep 5%. So that's quite good for them. So part of the Kickstarter was to make little microcontroller boards and give them to people as rewards. And we went to a local PCB assembly house in the UK, in Luton. And they were very helpful and friendly, and they really wanted to work with us because they thought, okay, so Geltech is more of a, like, they work with space projects and parts of the LHC, the collider in CERN. And they wanted to get more into direct-to-consumer things. So they thought, okay, if we partner with Damien here and build these little boards, maybe we can get insight into more of the consumer side of things. So they were really keen, and invite you and give you lunch for free and so on, and show you around the factory. And it's really great to see inside a factory and see all the machines moving. And I think when we said, oh, we need to make 3,000 of these things, they said, wow, that's normally they're used to like 100 or 200, but of some massive, say, car charger or something. So doing 3,000 was a lot for them, although they were obviously per unit, it's a very small cost. But so it was a bit of a challenge. Well, it was a learning curve for them as well to get this many units shipped. But since up until to date, we've done about 13,000 plus boards with them, and yeah, they've been very good. And it's definitely worth working with a local manufacturer rather than someone from China, just because communication is so much easier. I literally just drive an hour and visit them, and it's been really good. Okay, so but delivering on the Kickstarter, I don't know if you've ever done one or if you've know someone who's done one, but actually sending out 2,000 things is a long and arduous process. In this picture here on the left, I think there are 4 PhDs just sitting and packing. So you send a lot of stuff, and yeah, you get friends to help. Okay, so as I said at the beginning, the reason that I couldn't just take CPython was because the memory consumption is too high. And so all of the tricks that I've put into MicroPython are in order to reduce the memory consumption. So, okay, strings are interned, which means you make a string immortal, and that helps with efficiency and also memory usage. So the way numbers are fixed up so that they don't use heap memory is that you actually stuff numbers into a pointer, and I'll explain about that on the next slide. And this is a trick from Lisp from a long time ago. There's optimizations for the method calls so they don't use the heap. For loops don't use the heap, they use the stack instead. And lots of things where possible will live on the stack instead of allocating memory on the heap. And everything else that is sort of an object, sort of statically allocated like a module, that actually goes in ROM or in flash, in read-only memory. So when MicroPython starts up, it's almost instantaneous because everything is already pre-computed and stored in the read-only code section. So that's also a very important trick. Yeah, and it doesn't use reference counting like CPython in order to save memory. So it uses garbage collection only. And there are exceptions that are implemented using sort of set jump, long jump, if you know what that is from C. This is just a little diagram about how the internals of the compiler and the virtual machine work. So On the left-hand side is sort of the compile stage. So the scripts go into a lexical analyzer which tokenizes, and then that turns it into a parse tree, and then the compiler runs through the parse tree and annotates it with some type information, a number of local variables and so on. And then eventually it emits bytecode. And then on the right-hand side of this diagram, the virtual machine there executes the bytecode, and it uses helper functions to do things like, you know, insert things into dictionaries or search for stuff in a string or concatenate strings, and do other things like that, lists, raise exceptions. And then that can call any external C code or any other language down the bottom right there. And then you can actually generate code and recompile it within itself. So it's a fully dynamic language. The compiler can also emit native machine code, sort of like ahead of time compilation. And I'll explain a bit about that coming up. So here I'm trying to explain how this pointer stuffing works with integers. So this, as I said, is an old idea from Lisp. Maybe, yeah, I think Lisp pioneered it. So say we have a 32-bit machine, and we have a pointer, we have a 32-bit word, and we want to get the most out of this word. So if the least significant bit is set to 1, then the 31 upper bits actually represent an integer. So I have 31 bits to represent an integer, say from -1 billion to +1 billion. But if that lowest bit is actually 0, then I've got those higher bits can store something else. And actually we use a scheme where if the lower bit is 0, you then have to look at the next bit. So if the next bit's 1, it's a string. If the next bit's 0, then the upper bits are actually a pointer. Because pointers are aligned to 4 bytes, just the way objects have to be aligned, this doesn't lose any address space at all. So if the 2 lowest bits are 0, it means that your 32-bit word is actually pointing to something like a list or a dictionary or a floating point number, for example, or a class. And in this way, you're really using up as much of the space, the coding space in this 32-bit number as you can to efficiently store your numbers. So if I do 1 plus 2, then the information is all just stored in the actual pointer itself, which lives on the stack, or it lives literally within the actual list. It doesn't actually have to store on the heap anywhere. So this is the main trick that you use to not need to use the heap so much. And there are other schemes you can use to sort of stuff 30-bit floating point numbers within a machine word as well. And then there's also this thing called NAND boxing, where you use 64-bit words, and then you can put in a 64-bit double precision number, as well as integers, as well as pointers, as well as strings. So you're really trying to use up this space as much as you can. Okay, so that's one of the main tricks. So now I'll just talk a little bit about the bytecode that comes out. So this function here just adds 2 numbers together, and on the bottom of the screen is what it compiles to. So I load X, I load Y, so that's 0 and 1, and then I add them together, and then I return the value. And there's a stack machine, so you have a stack of values, so I load X onto the stack, I load Y. Calling the add operation will add them, and then the return operation will take the top of the stack and return that value. So this is the sort of the default way the compiler emits code. But you can also ask the compiler to emit assembly code, direct machine code, so that it runs straight away on the machine. It doesn't go through the virtual machine. And it may be a bit difficult for you to read, sorry, but it's anyway written in assembler. So it's the same function, but it's compiled to assembly. And essentially what I'm doing here is, I'll just go back 1 page. So each of these virtual machine opcodes is being sort of unrolled into its actual assembler. So it's sort of unrolling the virtual machine and what it would do if it was executing those bytecodes. So there's actually, I'm not going to go through this, there's a lot of prelude to set up the function to decode the keyword arguments and so on, and then the actual addition is sort of towards the end there. But it calls some runtime function. This is ARM machine code, if you're wondering. Anyway, it's just to show you that it's possible to, if you want extra speed, you don't want to go through the virtual machine, you can compile ahead of time. It's not just-in-time compiling, because you have to specify beforehand that you want to use this particular output from the compiler. Okay, so just a few words on coding style. So I have a research background, and to me, MicroPython is sort of like a research project. It cannot even be done at all, and I didn't really follow programming practices that maybe you were taught in university. So I optimized first, because if it can't be optimized, it can't even work, right? The idea is that it has to be optimized to run on a microcontroller. There's lots of tricks that have to be used to sort of get things to fit and to run efficiently. Clarity of code is sacrificed to get smaller code, and you're encouraged to use GOTO whenever you can, because to make the code smaller, for example. Well, not encouraged, but GOTO is certainly not discouraged. So the idea in the coding style is a bit different to maybe what you're used to, and I mean, it's just a remark to tell you that it's kind of like, it's a lot of fun, and I think went into coding MicroPython. There was also a lot of analysis to see, analyzing millions of lines of Python code to see what the most efficient way of decoding the bytecodes were, for example. There's just this little code dashboard that I set up to track the size of the code and the speed of the execution. So the red fuzzy line is actually the speed, the number of PyStones that MicroPython gets. So this is just to make sure that we don't suddenly double the size of the binary or slow it down so much. So MicroPython is an open source project under an MIT license, so you can use it however you like. And it's developed in the open on GitHub. And GitHub, I mean, I'm sure most of you know and probably use GitHub. It's an amazing community of programmers. I mean, it really is sort of like the social network of coders and developers, and it's been very, very good for MicroPython because it attracts people, people can contribute, raise issues very easily, and it's gotten quite popular, got quite a few stars, and in the top 0.02% of all projects, although there are 10 million projects, but you can work out what top 0.02% is. So I think having it on GitHub and having such feedback from people running MicroPython on so many different machines, like this old, say, embedded system that has a GCC compiler version 3, for example, makes the code more robust because people can give feedback from these systems. Okay, so just to give you a quick overview of the sort of sizes that it runs on, the PyBoard, which was the hardware that we make for the Kickstarter, it has 192K of RAM and 1 megabyte of ROM, or flash, and runs at 168 megahertz. And there are a few other numbers there from other systems. But it can also run on your desktop as sort of a lightweight Python implementation, if you like. For example, in the OpenWRT project, which puts Linux on like these little router chips, they have a MicroPython package if you want to run Python on that system. And the desktop version is also useful for testing. So instead of downloading to a microcontroller every time you want to test, you just run it on your computer, and it runs the same. Okay, so I think for me, one of the most exciting things was working with the European Space Agency. What actually happened was, a couple of years ago, so the start of last year, I think it was, someone from the European Space Agency emailed me and said, "Do you think MicroPython could run in space?" And I didn't even have to think. I was like, yes, I think it can. And but anyway, that led to, and they said, okay, well, we would like to do a project with you to sort of essentially set up a contract and a project to do a feasibility study to see if MicroPython can run on space hardware and within the constraints of space systems. I mean, I learned a lot about how space systems work. So, for example, they use Spark CPU, which is a kind of an ancient thing, but that's actually pretty cool once you get used to it. It's a RISC instruction set and a lot of fun to work with. And the Leon implementation of Spark is sort of an open source version of Spark, a description, and Leon is the microcontroller and Spark is the CPU. And RTEMS is the real-time operating system that runs on top of that. So this is what ESA uses in a lot of their payloads in missions, for example, satellites, and the Planck satellite that discovered the CMB, or well, got very good images of the CMB. So lots of their systems run RTEMS, which is a very highly tested and qualified piece of code. And the idea was to get MicroPython running within RTEMS as a little task, so that you could, for example, say, okay, we've got a virtual machine we bring up, and we're going to upload some code from Earth to this spaceship, and so a script, and then it's going to run some sort of thermal control thing to check all the parameters of the spaceship, and then print out some statements depending on what the parameters were like. So the idea was to see if you could use MicroPython as sort of an applications level language on spacecraft to enable more rapid development of coding. And that went very well, and it seems that that's possible, and we may have a few more ongoing contracts with ESA to qualify MicroPython to make it sort of space grade and actually use it in real missions. But yeah, this is sort of a few years planning, but it's very exciting. The other exciting project was with the BBC. So they have this microbit project, which is this little controller board. And so they made the BBC Micro many years ago, like the Commodore 64, and they want to sort of reignite that sort of idea by making an IoT device, the microbit, and inspire children to get back into programming. So they've given away 700,000 to 800,000 of these to all 11-year-olds in the UK, and the microbit here can run different languages, and MicroPython, or Python via MicroPython, is one of them. So children will be able to learn programming using MicroPython on one of these devices. And we're getting some good feedback there, but there's still a lot more development on that to go. Okay, so getting to sort of the IoT part, so we did a second Kickstarter, which was based on this Internet of Things chip, the Espressif ESP8266. It's just a, I have one here. It's a little chip that costs about, a few dollars. You can get it from China, and it's got just enough memory to run MicroPython. It's got about 96 kilobytes of RAM, although a lot is used by the operating system. And we did a Kickstarter to say, okay, if people want to have MicroPython running on this chip, here we'll take some donations and then we'll code for you and do it. And so I partnered with some other developer who is very keen on MicroPython, and we managed to raise almost £30,000 on a pure software campaign. So it was basically saying, if you're interested in having this software work, this free open source software, then please fund us. And we got such an amazing response. I didn't expect to get anywhere near that much for a pure software campaign. And if anyone here has backed the project, thank you very much. But it was really exciting. And I'll just give a few live demos now, hopefully, that will work, about this, with this chip. Okay, so I know there's, you probably can't see too much, but you can come and look at it later, but it's a little thing here. And I will just attempt to change screens. Okay, here. Okay, it works. So I will reset this. Now, okay, some garbage is printed to the screen. Can we all see this? Yep. Yeah, it's okay. So here, there's a bit of debugging output, that's okay. So here, MicroPython, so all I'm running here is a terminal emulator. It's just connecting via a serial prompt to this little board here. So it's just it's a UART, it's just sending and receiving characters. My computer's not doing anything except sending and receiving characters to this device. And you can see here I have a Python prompt. So this prompt here is on the board. So there's a bit of information about the version up there and so on. But I can actually type in Python commands. So things 1 + 2, it gives me 3. Although I'm sorry, we'll see if I can adjust the screen for you. Open another terminal. That's better. Okay. Okay. So this is a Python prompt running on the board. So if I'm typing something like then this gets compiled and executed on the little chip itself, and then the response is printed back up the serial port. So the computer is not doing anything except sending and receiving characters. So there's things, there's floating point support, for example, and maths. There's a math module. Oop. Square root. Okay. There's big number support, so say 2 to the power of 100, 2 to the power of 100, or 2 to the power of 1,000. Yep. Okay, so it's full on. There's a seamless transition between small numbers which fit in a word, like I was saying before, and long arbitrary numbers. So it's a full, well, MicroPython is not full Python because otherwise it wouldn't fit. And the aim is not for MicroPython to compete with normal Python. The aim is for MicroPython to allow Python to run where it couldn't run before. So we have to, in some cases, sacrifice some features. And a lot of the standard library that you normally expect with Python is not there. But nevertheless, I think the language, the syntax is still 100% complete. So there is lots of things there. We have, for example, if you want to see, sorry, it's quite hard to type it. So here I can show you the amount of memory and how it's being used. So the stack, there is 8 kilobytes of stack, if you can follow the mouse, and about 2 kilobytes is being used. And the heap, yep, so there's 28 kilobytes of heap, and then this here is a representation of what's being used on the heap so far. This is just for information. So, and then the thing with this chip is that it has network capabilities. So the actual chip itself has this little antenna here, and well, that connects you to Wi-Fi. And MicroPython tries to give you really easy access to the network. So let's import the network module. Okay, I hope everyone can see okay there. And I can, so interface naught is network.wirelesslan0 if naught.ifconfig. Okay, so this is my IP address, netmask, gateway, and DNS server. This is on the local GOTO Amsterdam network. So this is, I can connect to other networks, if-naught.say connect, and then just give my SSID and my password and it will connect. So this is how I've connected to the network. And then one of the goals of MicroPython is not to reinvent anything where possible and to reuse all of the existing Python libraries to do things. So if I want to connect to the network, I use the socket module in Python, or from a low-level point of view. So the socket module is there, and so say I want to look up, so notice I have tab completion as well, so that's how I'm typing so quickly. Yeah, pressing tab will complete, and it's useful for working out what functions are available. So I can say get the address of this website for this conference. Okay, so that's looking up a DNS server. Okay, so let's do something a bit more interesting with our network. So remember, this is all running here on this little chip here with about a 28K heap doing all of this. So I have some pre-made little demos. So I have paste mode here, which allows me to easily cut and paste some code. Okay. So this is a simple demo that tries to download the Star Wars ASCII-mation. And so it's quite straightforward. It's just, it looks up this web address here. And port 23 is the telnet port. So we open a connection down here, create a socket, connect to our address, and then just while true, receive information from this socket. Just get as much as we can from it, and then print it out to the screen. So it comes in as binary data. I have to decode it as UTF-8 because it's Unicode. And I don't want to have any line endings. And so this loop here will just continue running. So when I've entered this code here, okay, so now that code's running. It's downloading. It's connected via a telnet to this server, and it's just downloading and printing the text as it comes off the server. So I don't know if you've used Star Wars ASCII-mation before, but if you just telnet into that address, you can watch Star Wars. It's quite cool. So this will just, well, we'll keep running for probably, I don't know, I've never watched the whole thing. I guess it runs for hours. So anyway, but this is, you can see that, okay, so I just Control C, and it will break out, and I'm back to, I get a keyboard interrupt like in normal Python, and I'm back to my prompt. So with that, that was 1, 2, 3, 4, 5, 6, 7, sort of 8 lines to implement that on this little device. So if you tried to do that in C, I mean, there's nothing stopping you. It just, the compile time, you have to write the codes probably 4 times longer, compile it, download it. If there's an error, go back and do it again. But using MicroPython, you have the prompt here, and you can just try things out very quickly. So prototyping is very quick. And that's one of the main aims. So I can do it, there's another demo here to just this function, Control E. Okay, so this function here is just to download a URL, HTTP GET. So it looks up the address, it makes a socket, and it sends a GET request for the web address that you like, and then it just does a little loop downloading and printing out that URL. Okay, so I have this function, HTTP GET, and I will, this is just a little web page that I use for testing on the MicroPython server. So there, I just downloaded it from the internet, our web page. So you can download whatever page you like. Now, of course, I've only got 28 kilobytes of RAM. I can't go and download, you know, a megabyte web page and store it and parse it. That's just a limitation of these things. But if you just want to read some JSON and send some JSON, that's super easy, and it will fit in memory. There's a JSON module which allows you to, so just this is a normal Python JSON module. So use dumps to convert, say, a list of numbers. And then, so I can load that back again. Underscore is the previous expression. Yeah, so that just reparsed the JSON. So you know, you have very powerful things at your fingertips: string formatting, dictionaries, hash tables, exceptions, and you can make some really simple web applications that way. So there's a few more things here I can demo. So some more hardware-oriented things. So I've got some code here which, so there's this module called the machine module which gives you access to hardware, for example, the pins, GPIO. So I've created a few pins here, pin 0 and pin 2. And if okay, they're both on at the moment. I'm sorry that the lights are very difficult to see for you, but you might be able to see the red and the blue one are on. And so I have P0 is pin 0, and I can make that low, and that will turn, okay, that actually turns it on because the LED is wired inverted. And high, if I can type properly. Okay, high is supposed to turn it off again. Okay, so the red one went off. If I go low, it'll go on again. And if I go high, it will go off again. Okay, it's off now. And okay, the other big part of this demo. So I've made a function here which allows to pulse using sort of pulse width modulation. So if I want to pulse pin 0, LED 0, with say, well, this is my delay. Okay. The little red light will flash, and if I increase the delay to say 2 milliseconds, it will flash slower. Okay. So anyway, you can come and have a look at this up closer if you want later. But if you can appreciate the code here is rather simple, just to do I/O. And there's a function here to do the pulsing. And you can connect this up to, say, internet. So in the sense of you can make a web page, and when you click a button, it can turn a light on. Or the other way around, the web page can tell you the value of some pins, the, say, analog or digital value of a pin. Now, I was actually I will try and do this demo. It wasn't working before, or it was at some point. the idea here is, okay, so this code I've just pasted here is supposed to make a little web server, and you as the audience are supposed to be able to go to the web page and turn lights on and off. But unfortunately, the network here, whilst this was downloading just fine, for it to actually act as a server, it wasn't working before, but I will try again. Okay, well, it's not working, but I'll tell you what it's supposed to do. So this is the IP address of this device, and 1 is getting LED 1, and I want to turn it on. So I just made a simple sort of API request here. So if I went to 0, if I can read, yeah, 0 on is supposed to turn LED 0 on. For some reason, this thing is not working as a server on this network. But you can see the code there. So it's just running in a loop, waiting for addresses, waiting for clients. And then this while true loop here is just parsing the incoming request from the web browser. So it goes through each line, and if it finds the get line, then it splits up the URL and sees if I want LED 0 or 1, if I want to turn it on or off. And so this bit of code here detects if you want to turn it on or off and turns the pin on or off. Okay, so this is how you should be able to make some IoT device. I assure you it was working before. Okay, so I think I need to start wrapping up. I will go back up to my main slide and just say, okay, so well, in summary, MicroPython is, the idea is to bring Python to places it couldn't go before, especially in resource-constrained environments without much RAM, for example, on spacecraft or on little Internet of Things devices. There's lots of ongoing work, especially with this ESP8266 code. There's still lots of stuff we need to do for the Kickstarter, including some async I/O support. You may have heard about async I/O. It's coming out in lots of languages now. I think even the latest version of JavaScript has it, and we're going to support that as well because Python supports it, so we want to support it. Multi-threading support is nearly finished, so you can actually run multiple threads as you do with lots of other languages. And yeah, there's lots of other ongoing work with the microbit, more work with ESA for further space embedding, and also the idea is to make MicroPython easier for someone to just take and use in their own project. For example, if you wanted to add some scripting capability to a game, and you wanted that scripting language to be Python, then you could just take MicroPython and sort of chuck it in your system without any difficulty at all, and it would just be integrated. So that's another application. So don't forget to rate this session like all the other sessions, and thanks for your attention.
Well, Damien, thanks very much for your presentation, and it's quite an impressive feature what you achieved with MicroPython running on such a small footprint. So thank you for that as well.
Thank you.
I got some questions from the public, and someone asked, when do you decide to use Arduino C or MicroPython or embedded C? Do you have some pointers on that?
Arduino C or embedded C?
Yeah, or MicroPython, if you have to choose between it or between the use cases. Okay.
Yes. So. MicroPython can't run on really small devices. Like it needs at least about 256K of flash. And on Arduinos, you have really very limited, probably 16, 32 kilobytes of flash and 1 or 2K of RAM. So MicroPython can't go down that far. So if you want really cheap and low power, so remember the reason you use a microcontroller is because it's cheap in volume and it's very low power. It runs on a battery, unlike a Raspberry Pi. And if you want something like in a toaster, you'd probably just write in Arduino or C. I mean, Arduino is essentially C++. So if you're making a toaster, I'd say you use C. If you want to make an internet-connected fridge or coffee machine, you probably use MicroPython. But yeah, it depends on the size of the microcontroller really and what your need is.
Okay, thank you very much. Someone asked, do you know the G-Ling, the Java-like VM microcontroller?
Sorry, which one?
Yeah, it's the Darjeeling.
No.
It's a pretty complicated word. No, I don't know it either.
But please, well.
Yeah, please walk up if you have a question about it.
Yeah, sorry, I don't know that.
And someone asked, is there already an in-production solution with MicroPython that you know of?
I do know that there are actually coffee machines that were using MicroPython. Although I don't know the name of the brand, but there was some help I was giving to someone who was trying to get an IoT, internet-connected coffee machine. It's being used in teaching. There was a university course that was set up around it to help teach undergraduates about computers and other commercial applications. I'm not aware of that many. I do know lots of people use it, but I don't have really any way to keep track of what they use it for.
Okay.
Being MIT licensed, it's out there in the wild and people do what they like with it, which is good. Okay. But yeah, more feedback from people would be nice. And
one last question, what's the future for MicroPython?
So, well, I don't know. I mean, for me it was an interesting exercise, and now it's grown into a really nice open source project that lots of people are contributing to. And I'm just happy to be able to contribute finally to some open source project, because I use many myself, for example, Vim. And so I just hope that it can grow and actually find good use and a sustainable community. I think open source projects are hard because it's easy for them to die if they don't have someone working full time or they don't have a community that picks it up. So I hope that, I mean, so far it's been really great. There's a very big community, well, there's a relatively large community around it who is very supportive. So I just hope that that continues. That's my main hope for the future.
Well, I hope you reach something public today. Damien, thanks again for your great presentation.
Okay.
Blik applaus.
Thank you.